Okay, so welcome to another video on rotation. We want to talk about torque. When you say torque, you mean torque of force. You also mean about an axis. So let's take in a demonstration of something that we want to exert force on. Say here is a wrench. I want to exert force on the wrench so that I'm trying to tighten a nut here. So if I'm trying to tighten something there, I need to rotate it this way. So I need to apply force that way. I can apply force various places, but I know from experience the further away I apply a force, the greater the impact. And that's what the torque captures, the impact of my force in the rotation. Okay. And so let me write down some definition of the torque. So here is a basic definition. Here is something I'm trying to rotate about. So axis is very important. So this axis, this notation, the axis means axis is coming out of the board and in that direction. So this imaginary line coming out like that. And say I apply a force, that's in this direction and at that point. So apply a force F. And this distance is L. Okay? So I want to know how much torque this force will be. And all of this line and this line are in the same plane. Okay? So this, if you say this vector, R vector and F vector, R vector and F are in the same plane. So they're all, if you wish, you can just say this is, when I draw this diagram, they turn out to be in the same plane. And we're going to do, for simplicity, if they're not in the same plane, we're going to talk about that also. So this is in the same plane. Okay, so same plane. When that happens, there are a couple of ways we can define the torque. One is, the one that I really like is called lever arm. Okay, so this force, we associate what is called lever arm. So definitions, so one is like using lever arm. So lever arm is a concept which associated with the direction which force is acting. So force is acting along that direction, right? So so go to the force and draw a line as long as needed. Okay, so this is called line of the force. So each force that you work with will have its own line, and then I go to the axis point, which is in the same plane. Okay, and from there I draw a 90 degrees to it. So you can see that this distance I could compute using the geometry of the situation, right? This distance is called lever arm. So each force will have its lever arm. So if I have this R, which is over here is L, that's L, we need to figure out this. So I have this right angle triangle to work with, right? On one side is known. So if I know any of the angles, so if I know this angle already, we already know this angle. So if I know this or this angle, all be done. Well, when the force is given, maybe force is given this angle. This angle is usually given at what angle the force is acting. So suppose this is given. say this is theta, then by this cross of the two straight lines, this will be theta. This will be theta. So now this triangle tells me that lever arm here is L times, what do you think? I think this is going to be sine theta, right? Because this is opposite. So over here I found lever arm, which we're going to use this symbol R sub perpendicular because I have to draw a perpendicular, just a notation. Over here I got a formula, L sine theta. Now this may not be sine theta. If I was using this angle, so suppose somehow I knew this angle and not that angle, so suppose this was phi, will be L cosine phi. So depending on which of the angle you're going to work with, you're going to use cosine or cosine. So if you are really all the time using sine, you're working with this angle, you're going to get wrong answers. That's why you have to work with the triangle you got and figure out which angle you know and which sides are involved. All right. A lot of people make mistake there. They memorize L sine theta, but when they work out the angle, they find this angle sometime, and they plug in here, and of course they're going to get a wrong answer, right? So when you use a lever arm, so first thing to compute is lever arm, and then you multiply the lever arm with the magnitude of the force. So the magnitude of torque which we use the symbol tau, like this is fancy symbol tau. Tau is equal to, take the lever arm of the force and multiply by the magnitude of the force. So magnitude of the force, lever of the force, magnitude of the force. I'll write like that. Because there's a lot of work I better make sure I got it right. And so I could decorate this with a F also, because this lever arm is not just, if you have two forces in the same problem, they will have different lever arms normally. They may have same just accidentally, but they may have different lever arms. So we got the magnitude, and third thing I need to figure out is what the torque is trying to do. Is it trying to rotate it this way or that way? And so with a sense of rotation of the torque. So if I look at the current situation is that if this is the axis and this is the only force acting, then this will try to rotate it that way. So here, so this will be a counterclockwise or clockwise, but in my example here it's counterclockwise. Okay, so I like this way of working out torque, and it's a lot of work because when you work with more than one force, you have to do this for every force. So what happens if I have two torques, okay, two forces? How do I get the net torque? Well, let me illustrate that. How do you get net torque? So if this is where the sense comes in. If one torque is trying to do clockwise, another is in counterclockwise, then you're going to have to subtract. If both torques are trying to do counterclockwise, then they will add. So you can say, I'm going to take a convention that the torques which are trying to do counterclockwise, I will use a positive number for that. And the torque which is trying to do clockwise, I'll use a negative number for that. So you can use that. So here is the illustration. Say if this is my axis now here, and let's do a very simple example. Let's say this is 30 Newton that way, and from here to here is 2 meter, and from here to here is also 2 meter, but I'm going to let's see 30 Newton that way. Okay, so I want to figure out, we're not figuring out rotation yet, just the torque. So you have two forces, and here's the axis. So I work out this force and I work out this force, right? So this force, if I make it as long as I need, and I drop from the axis, actually this is the lever arm, so I didn't need to do all the sine theta, etc. So I got so for, let's call it F1. So torque 1 became 30 times 2 times sine theta is 1. So has the magnitude 60 Newton times meter, newtons times meter, and it has a counterclockwise sense. So I need to keep track of what sense it is. I do this one, let's call this F2. Tau 2 is, well, I go to the axis, and on the line of the force, I drop 90 degrees. Well, this is the same, that's the lever arm, so it's 2 meters again. So I got a 60 Newton meter, and then counterclockwise. Well, both are counterclockwise, right? Both are counterclockwise. So the net torque will just add them together. The magnitude will add magnitude. So this is tau 1 plus tau 2 is 120 Newton meter, and it will have sense counterclockwise. There's another example where things are a little different, okay, is same simpler setting. Let's look at an example here. Again, same way, okay, but don't want to get us bogged into that. So over here, this one is going, again, 30 Newton, and this again 2 meters, and this is again the axis in the center. I have a pin, and I'm trying to rotate this, and let's again 2 meter, and let's do 30 Newton this way. Well, we already calculated this guy is 60 Newton meter and counterclockwise. Now when you this guy is clockwise, this is 60 Newton meter clockwise. So if this is plus, then this is minus. So the tau net is actually 0 here. You can say that this guy is trying to avoid that, this guy is totally balancing it, right? How about not balancing? So I have axis here, let's say 30 Newton and 2 meter. But suppose I 2 meter here, but again 90 degrees, but I have 20 Newton only. So this guy is just like before, 60 Newton meter counterclockwise. This guy is going to be 40 Newton meter, but clockwise. So this is plus and this is minus. When I add them, I get 20 Newton meter counterclockwise. This guy is bigger than that. Okay, so one more example will not hurt along the same lines, and let's work it out. So here's a, let's see, I got 20 Newton here, and this is 2 meters, and this again 2 meters, again 90 degrees, but this is 30 Newton this way. So this is exactly complement of this situation. Okay, so this one will give me 40 Newton meter because this is 90 degrees. So this is lever arm. So this is going to give me 40 Newton meter, and this is going to be counterclockwise. And this one is 60 Newton meter, but clockwise. So we always take this as a plus, this is a minus. When I add these two guys up, I'm going to have to subtract it, right? Because it's going to be 40 minus 60, so it's going to be 20 Newton meter. This is bigger than that, and this is going to be clockwise. So this is tau net will be like this. We will have more practice of lever arm when we do more problems. I'll do some more example problems later to illustrate the role of sine theta or cosine phi. Here the lever arms are very simple to compute, but when things are at angle, you really have to be very careful. It's not just the distance. Okay, so I'm going to stop here. Maybe this is enough for today. This was three or four videos for rotation. See you next video.